Okay, now that we've studied functions and we know what functions are, we're going to move on to something that we call function notation. Now, one thing that's kind of really important to know about this section is that while it seems confusing, or it may seem confusing, don't make it more than it seems. Really, this section is really about sort of the communication or the notation in mathematics, but the math that we're doing is not anything new. In fact, it's rather trivial, the math that we do, but it's actually the language or the notation that could get confusing. So in essence, what we want to do within this section is to be able to rewrite a function in what we call function notation. But once we have function notation, this is really the advantage of why we want to use function notation, is we want to be able to use it in calculations and evaluations. Now, the calculations and evaluations themselves do not change. It's just how we write it and how we sort of notate it within our work. And finally, the last thing we want to do, which is really nothing to do with function notation, I should maybe use this in section 1.1 when we talk about functions, but I didn't want to overwhelm with too much content in there. But what we want to do is be able to represent a relation using a mapping diagram. So what I wanted to do to start off with this section is just by an example. So here we're given an equation of y equals 2x plus 1. So a linear equation. And many times we ask the question of, well, what's the value of y, or how I phrase it, what's the answer when we're given the value of x equals 5? So I like to phrase this as the question. Well, when x equals 5, that's our question. What is our answer? So we would do something like this. We would say y is equal to 2. We just subbed in 5 for x. So 2 times 5 plus 1. So that's going to be 10 plus 1. So we see that y is equal to 11. Well, what happens if x is minus 20? So there's a lot of things in terms of computation, and when we have an equation, we want to know the value of y given the certain values of x. And you notice this is how we generate a table of values. We want to graph an equation and see what it looks like. So this question comes up often. So we would just show our work. Again, we'll say y is equal to 2, and we plug in 20 for x, or negative 20 for x, so 2 times negative 20 plus 1, so that's going to be minus 40 plus 1, which is minus 39. And the last example is x equals 100. So here we will say again y is equal to 2 times 100 plus 1, so that's going to be 200 plus 1, which is 201. So again, the math is not new, and in fact I would argue the math here is not hard. Now, one thing that I've reiterated over and over again is that mathematicians are lazy. They are super lazy. And because this is something that they would do often, over and over again, having certain values of x and then finding what the answer is or finding what the values of y are, they really don't want to write this part over and over again. X equals this, x equals this, x equals this. So if x equals a certain value, here's what we do. So what they've done is they've sort of invented or came up with a notation, what we call function notation. And so here's an example, is that the above function could be written in function notation as, so notice that really essentially what's happening is we replaced y with this thing of f brackets x. And that's what we call function notation. So here we're saying that we have a function called f. So that's the sort of name of the function. And sometimes you might want to think of it as a variable. It's still a variable. But this variable does not represent a value, but it represents a function. And what's this function dependent on? Well, they're saying that this function is dependent on the variable x. So that's what we have inside the brackets, is what function this variable depends on, or what really was the independent variable. And notice that in our equation, we must have that variable. It must be in here. So in here we have 2x plus 1. We would not have something like f of x is equal to 2t plus 1, because here we're saying that our function depends on x, but our equation does not have x in it. So we would never see something like that. Okay, if our equation does have t in it, we may see something like f of t is equal to 5t plus 3. So a variable must be in there. So that's the nice thing about function notation there. It makes sense. There's a direct correlation in there between the variable that's inside the brackets and the variable that's in our equation. So if we rewrite our function in function notation as f of x, and notice that there's a couple ways to say this. We could say f of x or f at x, and you may hear me use it interchangeably at times. So here f of x is equal to x plus 1. So because mathematicians are lazy, now they have a convenient way, and that's what this means in here when we say f of 5. Really, we're saying that whatever's in the brackets now, in this case 5, that's what we substitute or replace x with. So it's implied that the value inside the brackets is replacing what's in the variable. We don't have to say here, well, if x equals 5, it's implied because the 5 is inside the brackets. So in this case, we say f of 5 is equal to exactly what we did above, 2 times 5 plus 1, which is going to be 10 plus 1, which is 11. So likewise, notice that we have a shortcut here. We're applying that x is equal to minus 20 in this case. So that's going to be 2 times minus 20 plus 1, which is minus 39. So same as the answer we got above here. So notice that we're doing the same math. We're just representing or writing it down in a different way. So finally, the last example that we have tied in is f of 100. So here we're saying that x is 100. So here it's going to be 2 times 100 plus 1. And as we did above already, that's equal to 201. Okay, so that's really what all function notation is. Really in a simplistic form, you can think of it as, yes, we're replacing y with something else now. That looks a little bit more complicated, but actually is very convenient for us to tell us certain information. So now we've been given something else. Here we're saying that, well, f of x is 7. So what does that imply? And then we want to know what the value of x is. So even based on this question, we know that x is not 7, or at least we can't infer that x is 7. We're saying that f of x is 7. If x was 7, then we would actually say that f of 7 is equal to something, and we would just do everything we just did above. But that's not what this part is saying. It's saying that f of x is 7. So really, we're saying that the answer is 7. If we want to sort of see it in a logical way, again, if we write our function, f of x is equal to 2x plus 1. Well, really, we're saying that if f of x is 7, equal to 7, this is what I love about math. We're saying that the equality there, that 7 is the same as f of x and vice versa. So what we could do in here really is, if you want to try to remember it that way, so we could replace f of x now with 7. So two ways to remember this. We're either told, or remember that f of x is the answer. So in this case, the answer is 7. Or we could just do a straight substitution down there, and we get 2x plus 1. 7 is equal to 2x plus 1. And now we just solve for x. So that's sort of a hint, is that we don't know what x is. We have to go off and solve for it. So here we have a simple equation that we subtract 1 from both sides. So again, 6 is equal to 2x. And then finally, we determine that x is 3. And if we want to do a check of left side, right side, we could do that, or we just do that in our heads. 2 times 3 is 6. 6 plus 1 is 7. So f of x is 7 in that case. Okay, so that's all function notation is sort of really about. So a definition of it is function notation is a notation used to represent the value of the output. So I'm throwing some sort of computer terminology out there, but really it's what I think is the answer, or in this case, the dependent variable. So it's notation to represent the answer for a given value of the input, or in this case, the independent variable. For a function f bracket x, it is read as f of x or f of x. Either one works and is interchangeable. So let's go off and look at some more examples. So here we're given the function f of x is equal to x squared plus 1. So we can see that this is a quadratic. And now we just want to evaluate, well, what's f of 4? So again, the thing, in this case is a value inside the brackets, means that that's what we're replacing x with. So in this case, f of 4 is equal to 4 squared plus 1. So notice I'd actually put brackets around what the value of x is being replaced with. In this case, it doesn't really make a lot of difference because we know that 4 squared is 16 plus 1, so that's going to be 17. Okay, but in the next question, we will have f of negative 4. What's the value of that? The brackets makes a big difference. So here, we're replacing x with negative 4, but it is negative 4 that is being squared, not just 4 itself, because if we were to not write the brackets, we might mistakenly write this as negative 4 squared plus 1, which is a very different meaning because this becomes negative 16. Remember, the exponent only applies to what's to the left of it, plus 1, which would be minus 15, but that is incorrect because we know that negative 4 squared is 16 plus 1, and then it's 17. In other words, f of 4 is the same as f of negative 4. And in our understanding of quadratics, that makes sense. The last example was of f of 10. So again, we just plug in 10 for x. So here, I always do it, whether it's positive, negative, or this, just so that I get in the habit of wrapping things, whatever x is, in brackets. And we'll see that later on in further examples where that's really helpful. So in this case, 10 squared is 100 plus 1, and so that's going to be 101. So here in this example, we're given a graph of a function. So we could see that this is a function based on a vertical line test, and here we could basically go anywhere that's sort of vertical, a vertical line. Let me try this. Anywhere we have a vertical line, it crosses that graph at only one point. So again, that's the vertical line test that we could use to make sure that this function, in this case g of x, is indeed a function. This purple line, this vertical line that I draw, only crosses our graph only at one point as I move it across. Okay, so that's the vertical line test. So in this case, or in this situation, we're not given an equation. So how do we figure out what g of x is? Or more specifically in this question, how do I figure out what g of 4 is? Well, in the above example, we had an equation. We plug in x for 4. And that was actually kind of easy because the equation was easy. Well, in this case, we're not given an equation. We're given a graph. We could determine an equation for the graph. In this case, I would say for this one, it's actually very difficult. It doesn't look like anything is normal and anything that we studied before. But actually looking at a graph is actually pretty easy. What we're saying is that when x is 4, what is the value, or what's my answer, or what's the value of y? So we come across and we discover where x is equal to 4, and we go up and we find out where it intersects our line. In other words, what's the value of y when x is 4? And we discover is that point here, and we see that y is actually 1. So g of 4 is actually the value of 1. Another example is with g of negative 1. Well, same thing. There's x equals negative 1. So what's the answer there? And again, that's what the graph is. It's a pairing of x and y values, what we call coordinated pair. So what's the value of y when x is negative 1? Well, we can see that there's going to be 2. So g of negative 1 is equal to 2 here. So this is actually really a lot easier because we don't actually have to do calculations. We just have to be able to interpret the graph. So here's a little tougher question. What's the value of x, or determine x, if g of x is equal to 5? So here we're actually given the answer, or you want to think back in the traditional way, we're given y is equal to 5. So here we want to look at where y is equal to 5. So I'm going to draw a horizontal line. Here is green. So here is y is equal to 5. So in other words, what's the values of x at all the intersections where y is equal to 5 crosses our function here? So in this case, we see that in this function, there's actually 4 places where the answer is actually 5. So two are really apparent, so that's this one. So here we could say that x is equal to, in this case, minus 4. And the other one that's really easy to read is this one over here. And we can see that x in this case is 6. The other two are a little bit more difficult only because they don't fall in a crosshair, so we just have to make an approximation. So in this case, this looks like it's approximately negative 2.5, because it's sort of in between, almost in between the negative 2 and negative 3. This one over here is a little more difficult, so it's in between 4 and 5. I'm eyeballing it. It looks like maybe 3/4 of the way through, so maybe this is 4.75. Okay, notice that on there, I'm not going to look for an exact answer, looking for approximation. So as long as you're relatively close, you're going to get the mark. Okay, so that one's a little bit tricky because we're given the answer, g of x is equal to 5. We're looking for a specific x value where we have that answer. So here's another cool thing about functional notation that we can sort of work with is here we're given a function p of x is equal to x squared minus x. And we want to evaluate. It's kind of tricky because some of these things we're going to actually evaluate. It's more like simplifying. But in this case, what happens if x is a? So now it's not an actual value. But we still want to evaluate p of a given that p of x is this function. Well, again, what does that mean? Wherever there's x, we're just going to replace it with a. So here p of a is equal to, and again, I'm going to use brackets because we're replacing x with just a in this case, minus a. And here we could just simplify this to be a squared minus a. You could jump to this first step. I mean, this one's really easy, replacing x with a. But I just want to show that first part because we really want to take care, remember that really we're replacing x with whatever's in our brackets. And this is really important in the second example because here we want to figure out what p of a plus 3 is. So we need to replace x with a plus 3, and this is where brackets is really important because now we have a plus 3 squared minus, all in brackets, a plus 3. So notice that we don't have the brackets here, we're really going to mess up, and eventually I think you think you can get 0, but that's not what will be the case. Actually, not 0. It would be something like a minus a would be 0, and then 9 minus 3 is 6. So you might mistakenly think that p of a plus 3 is 6, when in reality it's not. Here we need to expand a plus 3 quantity squared. So it's going to be a squared plus 3a plus 3a plus 9. And again, minus, and I'll keep that in brackets as one expansion of a plus 3 quantity squared, and then minus a plus 3. So here we get a squared plus 6a minus 9. And maybe now distribute the negative, so we need to be careful of this. So that's going to be minus a minus 3. And finally, a final simplified answer in this case is going to be a squared. So 6a minus a is plus 5a. And then minus 9, positive 9, this should be a positive 9. Positive 9 minus 3 is 6. So that's going to be plus 6. Okay. So here's another example where we have a function within a function. So here we're given f of x is equal to 2x minus 3, and g of y is just 2y. So really whatever y we have, we're just going to double it. And so notice that here, remember I talked about the function notation, because y is my variable now, y must be in my equation. And notice that the name of my function here is g. So let's go off and determine f of 3. Well, f of 3, we just go back to our function f of x, and we'll replace x with 3. So in this case, this is going to be 2 times 3 minus 3. So that's going to be 6 minus 3, which is equal to 3. So now we could say something like, well, what's g of f of 3? So here we have a function within a function. So this is another powerful thing that we can do now that we have function notation. So what this really means is that we want to think about working inside the brackets and then working out. We need to determine what f of 3 is, and whatever that answer is, we want to take g of that answer. So in this case, we already figured out what f of 3 is actually 3, not the best example, but that's the way it works out to be. So this is really the same thing as g of 3. because f of 3 is equal to 3. Now we got to go back to what our definition of g of y is. So in this case, that's going to be 2 times 3, which is 6. Okay? So the last one is not so scaffolded anymore. We want to take g of f of 6. So we need to figure out what f of 6 is first. So let's go f of 6 is equal to 2 times 6 minus 3, which is 12 minus 3, which is 9. So therefore, g of f of 6 is really the same thing as g of 9. And we just remember that the g function is really taking 2 times our y value, or 2 times our variable inside. So this is just going to be 2 times 9, which is 18. Okay. And so finally, the last example is that we want g of f of 2. So again, we need to figure out what f of minus 2 is first. So f of negative 2 is going to be 2 times negative 2 minus 3. I think that was our function. Yeah, 2x minus 3. So that's going to be negative 4 minus 3, which is minus 7. And over here, so here we have g of f of minus 2. Well, that's going to be the same thing as g of minus 7. And this is going to be as 2 times negative 7, as that's what a g function says. And that's going to be minus 14. Okay, so not overly complicated. We sort of break it down in steps, working from inside outside, calculate the value of each function, and then once we get the answer, apply that answer to the next function. So now we're going to talk about relations and functions. So this is not anything about functional notation, but here we could represent functions in a different way. So one of the things that we've done already is talk about ordered pairs. So I used the example of mother and child, and that we could have as an ordered pair. But another way that we could actually do this is what we call a mapping diagram. And this involves directed arrows from each value, and we have ovals. So we have an oval to represent the domain and the oval to represent the range. So when I did the mother and child example, I had it separated, and I think I implicitly drew a circle around it anyways to group it. So where there's a circle oval, the fact is that we want to see a distinction between the domain and the range. So in this example, we're given a function, or sorry, let me even say a relation. And the relation is really 4 sets of points. Okay, remember this is not connected. We have no way to understand how this is these points are connected because it's not an equation. We're just given this 4 sets of data. So here we can say this is my x. So what are my x values? And what are my y values? So this is the domain. Remember, x is my domain, my independent variable, and y is my range. So my x values here are going to be 1, 2, 3, 4. And then what are my y values? In this case, we have, again, because it's a set, doesn't have to be in order. So I'll just list it out numerically. So it's going to be, oops, not 3, but I have 8, 9, 10, and 11. Okay. So here, we can determine whether it's a function or not one of 2 ways. So if we're just given a set of points, one of the things that I kind of hinted at in the last section was if our x is repeated inside our data points, or inside our points, then we know that's not a function. Okay, because basically what we're saying that for a given value of x, there are 2 different y values. So even looking at this set of points, I know that this is going to be a function because for every single x value, they're all unique. Now what a mapping notation does is we draw an arrow. So in this case, what's the corresponding y value to my x value? So here, when x is 1, the answer is 9. When x is 2, the y value is 8. When x is 3, the y value is 10. And when x is 4, the y value is 11. Okay, that's all mapping diagram really is. The nice thing about once we have a mapping diagram is that it's really easy to tell if this relationship is a function or not. And how we could tell is that for each value of x, how many arrows are coming out of it. And if And if there's only one arrow for every single x that's coming out of it, in other words, only maps to, and this is why it's called mapping diagram, only maps to only one value in my range, and it only has one answer, then it is a function. Okay? If, let's say that I had another point in here, let's say 2 comma 12. Okay, so we wouldn't write 2 again in our domain. So that's the thing about sets. You don't things are only happen once, or they're unique. There's no duplicates in there. We would add a 12 within my range. Well, let me put that within the circle. So let's say 12, that's in here. So in this case, 2 will map to 12. Sorry, yeah, 2 will map to 12. So right here now, we could tell that this is not a function because there's 2 arrows coming out of 2. In other words, 2 maps to 2 different values, and that's not a function. In other words, there's no definitive answer when x equals to 2. Okay, so here's an example where we use mapping diagrams. So the first thing we're asked to do is write the set of ordered pairs of the relation and then state whether the relation is a function or not. Well, I'm actually going to do the second part because I find that's going to be a little bit easier. So here I'm looking at the arrows coming out of here, and I see that while 15, there's 2 arrows coming out of 15, in other words, 15 maps to 2 different answers, so this is not a function. The second example, so this one looks kind of tricky because everything's pointing to -2. So is this a function or not? Well, we could have the same answer over and over and over again. So remember that our child-mother relationship, several children can have the same mother. So in other words, they will all point to the same mother. So therefore, by that we know that's a function because a person can only have one biological mother. So that's the same idea here, is that no matter what our domain is, no matter what a value of x is, 1, 2, 3, or 4, we get the answer 2. So this is still a function because only one arrow is coming out of each thing in my domain. So here, let's write the coordinate pairs. So in this case, this is going to be -8, 7. -1 maps to, in this case, 9. 0 also maps to 9. And then this is where we discover that it's not a function because 15 maps to 7, but 15 also maps to 9. Okay, so that's the set of ordered pairs. For B, the set of ordered pairs, in this case, well, everything maps to -2. So 1 maps to -2, 2 maps to -2, 3 maps to -2, and finally 4 maps to -2.